The last thing we're going to talk about in this section are the cofunction identities. They are listed in the box at the top of page 8. So I'm going to read through them and then we'll start working with them. The first cofunction identity states that the cosine of 90 degrees minus theta is equal to the sine of theta. The second one says that the cotangent of 90 degrees minus theta is equal to the tangent of theta. Next, we have that the sine of 90 degrees minus theta is equal to the cosine of theta. The next equation says that the secant of 90 degrees minus theta is equivalent to the cosecant of theta. The fifth identity says that the tangent of 90 degrees minus theta is equal to the cotangent of theta. And the last one says that the cosecant of 90 degrees minus theta is equivalent to the secant of theta. Okay, the note underneath says that these equations remain true if you replace 90 degrees with its radian measure of pi over 2. So for example, equation 1, you could use it as cosine of pi over 2 minus theta is equal to the sine of theta. Okay, where do these equations come from? Well, they basically come from the difference identities, because if you notice in each one of these, we are subtracting. Okay, so I'll illustrate with the first equation. Okay, where do we get this from? So if I have the cosine of 90 degrees minus theta, all I have to do is apply the difference formula for cosine, because I have cosine of something minus something. So if you go back to page 1 and look at your sum and difference identities, actually I already have the correct equation highlighted. Okay, we're going to apply equation 2 here. Okay, so if we do that, and I'll write it above, we know that the cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. Okay, if we match up the left-hand sides here, cosine of A minus B with the cosine of 90 degrees minus theta, we can see that A is going to be 90 degrees, B is going to be theta. Remember, the minus sign is going to be taken care of by the formula itself. Okay, so if we expand the cosine of 90 degrees minus theta according to this identity, we're going to get that the cosine of 90 degrees times the cosine of theta plus the sine of 90 degrees times the sine of theta. Okay, that is what the cosine of 90 degrees minus theta is equal to. Okay, we are left with two quantities that we know, the cosine of 90 degrees and the sine of 90 degrees. If you go to the unit circle, okay, we know 90 degrees is the same thing as pi over 2, so we need to look at this ordered pair 0, 1. So the cosine of 90 degrees is 0. The sine of 90 degrees is 1. We can pop those values in. So here we're going to get that the cosine of 90 degrees is 0 times the cosine of theta plus the sine of 90 degrees, that's 1 times the sine of theta. And then in the next step, 0 times anything is 0, so that goes away. We're left with 1 times the sine of theta, which is just the sine of theta. Okay, so that's where this first cofunction identity comes from, and the others can be obtained similarly. Okay, what we're going to use these guys for in this section, we're going to use them to solve certain types of equations. So let's take a look at example 9. We are going to find one value of theta or x that satisfies each of the following. Okay, so if you kind of peruse this example, we have 3 equations that we're going to solve. Either the variable will be theta or it will be x. So you need to find one value of the variable that makes the equation true. Remember, trigonometric functions are cyclic, they keep repeating, so you can have, multiple solutions to one equation, but we just need to find one solution here. All right, let's take a look at the one in part A. We are trying to find the value of theta that makes this true. The sine of theta is equal to the cosine of 2 theta plus 30 degrees. All right, so this could be a situation where you would use a cofunction identity to solve. Okay, if we go back through these guys, okay, we're trying to find a formula that relates the sine and the cosine. Okay, so I see this cofunction identity relates the sine and the cosine, as does this one. Okay, so the question becomes, does it matter which one you use? Okay, so let's talk about what we have. Okay, what's going to make this a lot easier to solve is having the same trig function on both sides. Okay, right now it's difficult to solve because I have sine equals cosine. It would be great if I had sine equals sine, or if I had cosine equals cosine. Okay, so that's what we're trying to use the cofunction identities to make happen. Okay, so notice we're gonna go with the less complicated part here. Sine of theta, it's the one that's the term that's not as complicated. Okay, if I go up to these two equations that I have highlighted in yellow, I see a match. I see sine theta right here. Okay, because I'm getting a match, I'm going to go with the first equation here. Okay, so this cofunction identity tells me that the cosine of 90 degrees minus theta is equal to the sine of theta. Okay, all right, let's see how we apply this to solve this equation. Okay, like I said, what's matching up? This matches this. Okay, so what we're going to do is go to our original equation, and we're going to replace the sine of theta with its equivalent. Okay, sine of theta is the same thing as the cosine of 90 degrees minus theta. Okay, I just made that replacement. I'm not going to change the right side. And now I have the cosine of something is equal to the cosine of something else. The only way this can be a true statement is if the somethings are equal. Okay, I'll repeat that. If you have the cosine of something equal to the cosine of something else, the somethings have to be equal. So I'm going to take the arguments and I'm going to equate them. Okay, the only way this can be true is if 90 degrees minus theta is equal to 2 theta plus 30 degrees. Okay, so I'm going to solve this equation. Okay, basically I need to get theta by itself, so I'm going to start by adding theta to both sides. That's going to tell us that 90 degrees is equal to 2 theta plus theta, that's 3 theta plus 30 degrees. All right, I'm going to move the 30 degrees over. I'm going to get that 60 degrees is equal to 3 theta, divide both sides by 3, and we get that theta is equal to 20 degrees. Okay, this is one value of theta that makes this a true statement. Okay, we can go to a calculator and check ourselves. Okay, if you go back to the original equation and you pop in theta equals 20 degrees, we're going to look at the sine of 20 degrees and we're going to compare that to the cosine of 2 times 20 degrees plus 30 degrees, which is the cosine of 2 times 20 is 40 plus 30 is 70 degrees. Okay, so if we look at the decimal approximations for these two guys, we should be getting the same thing. All right, so I'm just going to check myself. I always do that when I can. Okay, so if I go over here to my calculator, I'm in degree mode already. So I've got the sine of 20 degrees. Here's the decimal approximation. And now I'm going to look at the cosine of 70 degrees and I get an exact match. Okay, so I know that I am correct in saying that theta equals 20 degrees. Okay, all right, the next one. This time in part B, we're solving for x. We want to know what value of x makes this true. The secant of x is equal to the cosecant of 2 pi over 3. So you could start solving this equation by going to the unit circle and looking at 2 pi over 3 and figuring out its cosecant and then plugging in that number. That is definitely a viable path to solution. But again, I'm going to try to use a cofunction identity on this. I need an identity now that relates the secant and the cosecant. Okay, so if I go back up to my box, okay, let's see here. We need secant and cosecant. So this one would work. This one also, these two both relate secant and cosecant, but again, it's better to use one over the other, okay? So here, remember, instead of theta, we're using x. I am looking at this and I see secant of theta or secant of x. If I go back to these equations, I see a match. Okay, I see a match right here. Okay, this is secant of theta or secant of x. So I am going to apply this sixth formula over the fourth one, and when I write it down, I'm going to replace x with theta. Okay, so we're going to get that the cosecant, I'm going to be using that the cosecant of 90 degrees minus x is equal to the secant of x. Okay, so that is formula 6. Another thing I need to do before I can apply this formula is notice that I'm in radians because of the 2 pi over 3. So I'm going to change 90 degrees to pi over 2. Okay, I have to do that. All right, so this is the formula that we're going to apply here. Okay, remember, my goal is to have secant equals secant or cosecant equals cosecant. Okay, I can make my replacement. I know what secant x is. Secant x is the same thing as the cosecant of pi over 2 minus x. Okay, make that replacement. Okay, instead of secant x in my original equation, I'm going to replace it with the cosecant of pi over 2 minus x. That has to equal what's on the right. I'm not changing the right side. And now I have cosecant equals cosecant. Okay, so the only way a cosecant of something can be equal to the cosecant of something else is if my arguments are equal. So in the next step, I'm going to equate them. I'm going to put pi over 2 minus x is equal to 2 pi over 3. Okay, this is going to allow me to solve for x. Okay, I'm just going to get x by itself, so I'm going to add x to both sides. So pi over 2 is equal to x plus 2 pi over 3. I'm going to subtract 2 pi over 3 from both sides. And now I'm going to get that the value of x is going to be pi over 2 minus 2 pi over 3. So let's combine this into one number. Okay, these are both fractions that we're subtracting, so we need a common denominator. So multiply the denominators. 2 times 3 is 6. Okay, let's adjust our numerators. In the first fraction, I need to multiply the denominator by 3 to get a denominator of 6. So I will have to multiply the top by 3. So we will get 3 pi over 6. That reduces to pi over 2. I'm subtracting. Adjust the other fraction. Okay, to get a denominator of 6, we need to multiply by 2. Do it to the bottom and the top. So we will be subtracting 4 pi. And now we can subtract fractions. Okay, so just subtract across the top. 3 pi minus 4 pi is negative pi over 6. Okay, so that's going to be one value of x. That makes this a true statement. Okay, we can check ourselves by plugging in this x value into the original equation. So we need to look at the decimal expansion of the secant of negative pi over 6 and see if that matches the cosecant of 2 pi over 3. Okay, if I go to my calculator, I need to change over to radians. Okay, so the first thing I'm going to enter is the secant of negative pi over 6. Okay, so to do that, I'm going to do 1 over the cosine of negative pi over 6. There's the decimal expansion. Now I'm going to look at the cosecant of 2 pi over 3. That's 1 over the sine of 2 pi over 3. And I have a match. So I know I've found a correct solution for the equation. Okay, let's try one more. All right, the last one here in part C is the cotangent of theta minus 10 degrees is equal to the tangent of 2 theta minus 20 degrees. Okay, so this one's a tad bit different. When you looked at parts A and B, like you had in part A, you had sine theta. In part B, you had secant x. So you had a very simple argument. Both of the arguments here are complicated. You've got theta minus 10 degrees. You've got 2 theta minus 20 degrees. So it's not as easy, okay? So yes, we're going to have to go to a cofunction identity and match it up. We need one of the equations that relates tangent and cotangent. So it's either going to be number 5 or number 2, okay? So which one? Because we can't match it up with we don't see a cotangent of theta or a tangent of theta that we can match it up with. So we're going to do a little bit of work here before we can match it up. If you notice on the right, the argument, both terms have a 2, so I can factor that out. Okay, so I'm going to get that the cotangent of theta minus 10 degrees is equal to the tangent of 2 times theta minus 10 degrees. Okay, that's what happens if I factor a 2 out of the argument. Okay, you have to keep it inside of the argument. You can't bring it out. Okay, so what I can do now, because I'm seeing a match, okay, I'm going to name this something. I'm going to call it u. Okay, let u be theta minus 10 degrees. Okay, so now with this substitution, I'm going to rewrite this. Okay, I'm going to get that the cotangent of u is equal to the tangent of 2 times u. Okay, so now I see a cotangent of u popping up. Okay, so when I go to pick one of these cofunction identities, I want to match it with cotangent of u or cotangent of theta. Okay, so I need to use equation 5 here. Okay, so if I just switch the sides here, I'm going to get that the cotangent of theta is equal to the tangent of 90 degrees minus theta. Okay, so this is going to be the identity that I'm applying here. I need to change the variable. Okay, instead of theta, I'm going to be using u. Okay, so this is what my equation turns into. Okay, so at this point, okay, what I'm going to do, because remember, I need cotangent equals cotangent, or I need tangent equals tangent. Okay, I'm going to have to do some replacing here. Okay, we are going to have to look here. Let me put it in a different color. We're going to have to look here and here. Okay, because we have a match. Okay, cotangent of u is equal to 2u, and cotangent of u is equal to 90 degrees minus u. Okay, so what we can do at this point, okay, is equate these things because they're both equal to the cotangent of u. Okay, so we're going to get that the tangent of 2u is equal to the tangent of 90 degrees minus u. And now I'm happy because I have tangent equals tangent. Okay, so the only way the tangent of something can be equal to the tangent of something else is if the arguments are the same. So I'm going to set 2u equal to 90 degrees minus u. Okay, this is going to allow me to solve for u. So I'm going to move the u over. I'm going to get that 3u is equal to 90 degrees. Divide by 3. Okay, u is 30 degrees. Okay, I'm not done. Okay, when I look at my original equation, I need to solve for theta, not u. Okay, so I need to go back and make this replacement. I said that u is the same thing as theta minus 10 degrees. Okay, so we're going to replace u with theta minus 10 degrees. That needs to equal 30 degrees. So I'm going to solve for theta now by adding 10 degrees over to both sides. One solution is that theta equals 40 degrees. Okay, and we got this by using the cofunction identities. Okay, this was a tough one because the arguments were complicated. Okay, we can check on our calculator, go back to the original equation and replace theta with 40 degrees. Okay, so we're going to be looking at the cotangent of 40 degrees minus 10 degrees. So we need to look at the cotangent of 30 degrees and compare that to the tangent of 2 times 40 degrees minus 20 degrees. So we're going to be comparing to the tangent of, this is 80 degrees minus 20 degrees. That's going to be 60 degrees. Okay, so we need to look at these two decimal approximations and make sure they match. Okay, so I'm going to go back to degree mode here. All right, so the first thing I'm going to check is the cotangent of 30 degrees. Okay, so the cotangent of 30 degrees, that's going to be 1 over the tangent of 30. And then I need to compare that to the tangent of 60 degrees. And I have a match.